In this question, you can see that there is a rod of total length AB which is equal to 2L, and a temperature difference of 120 degrees Celsius is maintained between these ends A and B. Now another rod of total length of 3L by 2, this is L by 4, L by 4 and L, is joined at this end and in this end. So we have to find out the temperature difference between these two ends P and Q of the system. Now let us consider that the resistance of this part of the rod is R. So we can see that this circuit would be like that this would be 2R, because we have considered that if the length of this part is L by 4 and its resistance is R, then this length is twice as compared to this one, so its resistance would also be twice. So this is 2R, this one is R, this has a length of L, therefore it would be 4R, this is R and this is 4R, and this is again 2R. So you can see the system, and the temperature difference is given as 100 degrees Celsius across the complete system. In fact, 120 degree Celsius. Now you can see that the equivalent resistance of this one will be 6R into 4R upon 6R plus 4R, which is 10R. So this would be 12R by 5. Now we can say that this is the series combination of 2R, 2R and this 12R by 5. So we can consider that 2R and 2R is in series, so it would be 4R, and this 12R by 5 is also in series with 4R. The total temperature difference across these two is 120 degrees Celsius, and we have to find out the temperature difference across this one. So there is a simple technique that delta T can be written as that if we find out the ratio of 12R by 5 and 4R, then it would be 3 by 5. And if we add up these ratio terms, the numerator and denominator, then it is 3 plus 5, which is 8. So we have to divide 120 degrees Celsius by 8. And if we have to find out the temperature difference across this one, so we should see that the ratio of this one and this one is 3 by 5. So we can say that we have to distribute 3 parts to this one. So we are multiplying it with 3. So you can see that 120 divided by 8 is 15 and into 3 is 45 degree Celsius. So the temperature difference across this resistance only is 45 degree Celsius. Now we move on the next question. In this question, you can see that there are two conductors of same length, and this width is different, their thickness is different, which is D1 and D2, and their width is same. So we have to find out the equivalent thermal conductivity of this combination, and we can see that these are in parallel to each other. So this is R1 and this is R2. So in parallel combination, 1 upon R equivalent will be equal to 1 upon R1 plus 1 upon R2. And R1 will be L by Ka, where K is K1 and area is D1 into W. And R2 is L by K2 D2 W. Now 1 upon R equivalent. Now R equivalent will be the equivalent resistance of these two, and the length of that would also be L. The total area of these two will be D1 plus D2 into W. So it is D1 plus D2 into W, and equivalent conductivity is K equivalent. So R equivalent would be D1 plus D2. 1 upon R equivalent will be D1 plus D2 into W into K equivalent divided by L, and it would be equal to K1 D1 W by L plus K2 D2 W by L. Cancelling this L with L, W with W, K equivalent will be equal to K1 D1 plus K2 D2 divided by D1 plus D2. So the correct answer would be option number 3. Now we move on the next question. In this question, you can see that it is given that there is a heat of 1 calorie per second is flowing through a rod of some length. Let's suppose this is the rod and its length is L. So the dq by dt in this case, let's suppose it is I1, it is 1 kilocalorie per second. Okay. Now we have subdivided it into 4 parts. So the length of any one part would be L by 4. So you can see that if we draw a single part, then its length would be L by 4, but its area would remain same and its thermal conductivity will also remain same. We know that the heat current flowing through any heat slab is equal to dt by dx, which is the temperature gradient, into Ka. Okay, so this is not a different formula. In fact, dx by Ka is R. So I've written it in this form. So this is temperature gradient. So you can see that the temperature gradient is kept constant. It is given in the question that we have same temperature gradient. So if the temperature gradient is same, if dt by dx is constant, then we can say that I is directly proportional to Ka. And the thermal conductivity and area of cross section of each part remained same. So we can say that there would be no change in the amount of heat flowing per second through each of the smaller part. So the correct answer would be option number 3. Now we move on the next question. In this question, you can see that there are 2 slabs of same area and same length but of different thermal conductivity. So we have to find out the equivalent thermal conductivity of these 2. So we know that they are in parallel and the resistance Ra of the first slab would be d upon K1A, where A is the area of cross section, and resistance Rb of the second slab would be d upon K2A. The equivalent resistance of the combined slab would be d upon K equivalent into the total area, which is 2A, because for combined slab the total area is 2A, but the length is d. So we can substitute the value in the formula, which is 1 upon R equivalent will be equal to 1 upon R1 plus 1 upon R2. So you can see that 2K equivalent into area upon D is equal to, this is K2A by D plus K1A by D. So cancelling out A by D, we can write that K equivalent will be equal to K1 plus K2 by 2. In this question, you can see that there are 2 cylindrical conductors A and B, and both of them has the same material, but their diameters are in ratio of 1:2 and their length is in ratio of 2:1. The temperature difference between their ends is maintained same, and we have to find out the ratio of heat currents through the cylinders A and B. So we know that I is inversely proportional to R if delta T is constant, and therefore on the basis of this fact, this is constant. So therefore we can say that I is proportional to Ka by L, because R is L by Ka. Now you can see that K is same because their material is same. So IA upon IB will be equal to, this is area of B upon area of A into length of B upon, in fact, this is area of A upon area of B into length of B upon length of A. Now the area is pi d square by 4. So we can say that this is dA square by dB square and this is LB by LA. So dA square by dB square, the ratio of the diameters is 1:2. So it is 1:4 and LB by LA is 2:1. So this is the ratio of heat current and it would be equal to, now you can see that dA by dB is equal to 1:2. So dA square by dB square is 1/4 and LB by LA is 1:2. So this is 1:2. So the ratio would be 1:8. Okay, so the correct answer would be option number 4. Now we move on the next question. In this question, we can see that there are 5 rods of same dimensions and their conductivities are shown in the figure. It is given that there is no heat flowing through this central rod and we have to find out the relation between K. So this is a Wheatstone bridge and if there is no heat current flowing through this rod, then we can say that this Wheatstone bridge is in balanced condition. So let us name this resistance as R1, this as R3, this as R2 and this is R4. So R1 by R3 is equal to R2 by R4. Okay, so we already know that the area and the length is same and the resistance is inversely proportional to K. So we can say that K3 by K1 is equal to K4 by K2. So we can say that K3, K2 will be equal to K1, K4. So the correct answer will be option number 4. Now let us assume that the temperature of this point, this junction is T, and let us apply the nodal analysis. So we can write the equation as T minus 200 divided by R plus the series combination of these two resistance will be 7R by 6. So we can write T minus 18 divided by 7R by 6 and it would be equal to 0. So this would further simplify into 7 into T minus 200 plus this will be 6 into T minus 18 and divided by the 7R which is there, which is thrown in towards 0. So you can see that this is 7T minus 1400 plus 6T minus this is 108 is equal to 0 and you can see that it is 13T is equal to 1508. So T will be approximately equal to 116 degrees Celsius. So the correct answer will be option number 2. In this question you can see that a cylindrical rod has temperatures of T1 and T2 at its ends and it is given that the rate of heat flow is Q1. Now if we double all the linear dimensions, then what will be the rate of heat flow? So we know that rate of heat flow is T1 minus T2 divided by R, which is L by Ka. Now if we double the linear dimensions, then this area will be quadrupled, which is 4 times. So it is T1 minus T2 into K into 4A divided by, and the length is doubled, so it would be 2L. So you can see that this is twice of Q1. So the correct answer will be option number second. In this question, you can see that there are three rods. Each of them has same material, same cross section area, and are joined as shown. And these ends are maintained at these temperatures. So we have to find out the temperature at the junction T. So let us first of all apply the nodal analysis, and let us see that the linear dimensions of all the rods and the K thermal conductivity is same. Therefore, we can assume the resistance of all three rods to be same. So we can apply the nodal analysis and we can write down the equation as T minus 0 upon R plus T minus 90 upon R plus T minus 90 upon R. It is equal to 0. So 3 T is equal to 180. So T is equal to 60 degrees Celsius. So the correct option is option number second. In this question, you can see that there are two rods of equal length and their area of cross section are A1 and A2, and their thermal conductivities are K1 and K2, as well as their specific heats are S1 and S2. Now we have to find out the condition for equal heat flow. So heat current is equal to delta T by R, and in this question we have to assume that the delta T across both of the rods is same. So you can say that for equal heat flow, 1 upon R1 is equal to 1 upon R2, because when we will equate delta T upon R1 is equal to delta T upon R2, then delta T will cancelled out and R is L by Ka. Now the length is same, but A and K is different. So this is K1A1 upon L is equal to K2A2 by L. Cancelling L with L, the correct option will be option number 4th. In this question, you can see that there is a uniform slab of dimensions 10 by 10 by 1. It is kept between two reservoirs in such a way such that its largest surfaces are touching the reservoirs, and the temperature of two reservoirs are 10 degrees Celsius and 90 degrees Celsius. The thermal conductivity of this material is 0.8, and we have to find out the heat flowing per second through this slab. So the area of cross section of this slab would be the largest area, and it is 10 into 10 into 10 to the power minus 4. So area would be 10 to the power minus 2. The length of this block will be 1 into 10 raised to the power minus 2 centimeters, and the resistance R of this slab will be L by Ka. So L is 10 to the power minus 2 and thermal conductivity is 0.8 into 10 raised to the power minus 2 is the area. So you can see that R is equal to 10 by 8, which is 5 by 4. Now we know that heat current I is delta T by R. So I will be equal to 80 degrees Celsius upon R, which is 5 by 4. So heat current is 64 joules. Now we move on the next question. In this question, you can see that there are three rods A, B and C whose thermal conductivities are shown as shown in the figure. Now the total temperature difference between these two ends is this one, 200 minus 18 degrees Celsius, and we have to find out the temperature of this junction. So let us suppose that the temperature of this junction is T. So first of all, let us draw the diagram. Let us see that if the resistance of this rod RA is R, let us suppose that RA is R, then the resistance of this rod RB would be R by 2, because RA is L by KA and L area length is same and area is same. So the only difference is of K. So if the K of RB is twice, so RB will be R by 2 and RC will be equal to, RB will be 2 L by 2 K and RC will be equal to L by 3 K A by 2. So this is 2 R by 3. So this end is at temperature T2 which is 18 degrees Celsius and this end is at temperature T1 which is 200 degrees Celsius. The temperature of this end we have assumed as T. So we can apply the nodal analysis and we can write down the equation of nodal as T minus 200 upon R. This one is R. And you can see that the series combination of R by 2 and 2 R by 3 will be equal to 5 R by 6. So we can write down plus T minus 18 degrees Celsius upon 5 R by 6. Okay, so this would be equal to 0. So again, if I take LCM and if I take out R as common and I throw it out in on the other side of equal to, then this equation will be 5T minus 1000 plus it would be 6T minus 18 into 6. Now 18 into 6 is 108, so it would be equal to 0. So this is 11T and this would be equal to 1108. So T will be equal to 1108 divided by 11. So this temperature will be approximately T will be approximately 116 degrees Celsius. So the correct answer would be option number 2. In this question, you can see that there is a steel rod of K which is 42 joule per meter per second per degree Celsius, and this has a length of 1 meter. This one end of this rod is kept in ice at 0 degrees Celsius and the other end of this rod is kept in boiling water. The area of cross section of this rod is 0.04 centimeter square and there is no heat loss to the atmosphere. So we have to find out the rate at which the mass of ice melts. It is also given that the latent heat of fusion for ice is 3.36 into 10 raised to power 5. Now obviously we have to find out the resistance of this rod first of all. So resistance would be L by Ka. So L is 1, K is 42 and the area of this rod will be this is 4 into 10 raised to power minus 6. You can see that this is 0.04, so we can write it as 4 into 10 raised to power minus 2, and we have converted the centimeter square into meter square by multiplying additional term of 10 raised to power minus 4. Now this is the resistance, which is 10 raised to power 6 upon this is 168. Now you can see that the temperature difference delta T between the two ends is 100 and therefore the heat current dQ by dt will be equal to 100 upon R, which is 10 raised to power 6 into 168. So this is 168 into 10 raised to power minus 4. And this Q will be equal to 168. In fact, we can write down dQ as dm into L. So dQ by dt will be equal to dm by dt into L. So 168 into 10 raised to power minus 4 is equal to dm by dt into 3.36 into 10 raised to power minus, in fact, plus 5. So dm by dt will be equal to 168 divided by 3.36 into 10 raised to power minus 9. So this is in kilogram per second. So if we find out in gram per second, so it would be 168 divided by 3.36 into 10 raised to power minus 6 gram per second. So you can see that this will be 168 upon 3.36. So you can see that it will be 16.8 by 3.36 into 10 raised to power minus 5, and this is equal to 5. So it is 5 into 10 raised to power minus 5. So this ice is melting at a rate of 5 into 10 raised to power minus 5 gram per seconds. Thank you.